Welcome for today's live session for week 8 of economic operations and control of power systems. We will start with the overview of week 8 and we'll discuss all the points which were discussed in week 8 and then we will discuss some questions on numerical on LODF also. Well, it is similar to what has been given in the assignment. It requires some calculations that we will see how to do. So these are the deadlines. So tomorrow is the deadline for assignment 8 and 25th is the deadline for assignment 9th. So please submit it on time. And I hope all of you already have gone through this link and you're able to access the videos. We will start with the overview of week 8. In week 8, these two topics were discussed. One was this real-time case study on reactive power dispatch, and another was the power system related to power system security. So before doing that, it's understanding or going through that case study, the concept of reactive power, different sources and sinks of reactive power, and this real-time digital simulator, which is used for simulating these, validating the algorithms developed using integrating different hardwares as well as controllers. So that was discussed. We'll start with the different sources of reactive power in the power system. First is transmission line. And the transmission line, whether it will be a sink or source of reactive power, it depends on the loading of the transmission line. And it depends on the surge impedance loading. If the loading is more than the surge impedance loading, if it is inductive load, most of the loads are inductive in nature, industrial loads mostly. Even in now in commercial loads and residential loads also, because we have motors, pumps, we have water pumps at home and different motors, equipments which we use, all of them have motors. Most of them, they consume reactive power. So they are mostly inductive load. As a result, there is a voltage drop because of the reactive power absorbed by the line. If the line will absorb the reactive power, then there will be voltage drop, there will be a loss. Because this power is required to carry out the function. If a transformer, we'll see in the transformer next. So this loading, if it is greater than surge impedance loading, then there will be absorption of reactive power. As a result, there is a voltage drop. If it is equals to surge impedance loading, then there is unity power factor operation. The voltage profile is flat. Flat voltage profile, that means over the length of the transmission line. This is the length of the transmission line. And this is if this is sending end, this is receiving end. And it's a flat voltage profile. Voltage remains same throughout the line from sending to receiving end. But if the surge impedance loading is there, if it is loading is more than surge impedance loading, then there will be a voltage drop at the receiving end. And the opposite will be seen. There will be voltage rise in case of the loading less than surge impedance loading, which generally happens light loading condition, and especially in the EHV lines. It can also happen for short overhead lines if it is a weak grid connected to a weak grid. So this is, we already know, it is called Faraday effect. When the EHVAC or ultra high voltage lines, they are lightly loaded or open circuited, then the voltage at the receiving end, it increases, it rises, because the line is delivering reactive power. The capacitive element in the line, it is delivering reactive power. And to, if the voltage has increased, and if we want to bring the voltage back to its nominal value, then we need to absorb the reactive power which is being generated by the, or being delivered by the line itself. And for that, we use the shunt reactors. We connect a shunt reactor at the receiving end to again bring the voltage back to its nominal value. So this is transmission line. Similarly, underground cable, it is a source of reactive power under normal loading also, because of the capacitive element. The capacitance of cable is quite high because of the dielectrics. We have different armor sheath. In between, we have dielectric substance. Then insulation is also there. Between each layer, there are different dielectrics, and because of dielectrics, the capacitance of cable is quite high, and that's why it is delivering reactive power. Transformer, to set up a flux in the core of the transformer, it requires a magnetizing current. Even at no load, when there is no load, that magnetizing current is required, and that is equal to generate the flux within the core. And for magnetization of the transformer or the magnetic core, this is required irrespective of the loading of the transformer. And this is not going to be this reactive component out of the apparent power. If we the reactive component and then active. So this part, because of magnetizing current, is not available for useful work, which we call. And that is why we have only out of S, only this much active power is left with us. So without Q, we cannot operate the transformer itself. Mutual inductance, the principle of mutual inductance will work, and for that, the reactive power component is required. If it is not there, then we will not be able to utilize the principle of mutual inductance. And without using that, we cannot even transfer the power from one limb, the primary side, to the secondary side. So that is why Q is required to do to step up or step down the voltage, or even just to provide an insulation also. That part is of reactive power is utilized in transferring that, for transferring that power from primary side to secondary side. So here it is transformer, it's mostly inductive. Although there is no pure, there is no element which is without capacitance also. There are some stray capacitances, but mostly it is inductive. And there are some elements where we have capacitances also. In that case, that electros energy will be stored in that fields, in terms of electric fields. So we have irrespective of the loading condition, the transformer will always absorb reactive power, always. And synchronous machine, it depends on their excitation. If they are overexcited, then they will deliver reactive power. But if they are underexcited, then they will absorb reactive power. Synchronous condenser. The same synchronous machine, if it is operated at no load. At no load, then there is no. It will behave just like a capacitor when overexcited. The current will exactly lead the voltage by 90 degree. If some load is there, then this angle will not be exactly 90 degree. It will be less than 90 degrees. And if we use it at no load, then it will deliver only reactive power. And at no load, under overexcitation, it will act as a capacitor, and under excitation, it will act as a reactor. So it can work both as a shunt reactor as well as a capacitor. Because this the advantage of synchronous condenser. It was used when power electronics devices were not there. These SVCs were not available. All these things. Before that, synchronous condenser was used, where it was able to do the work of both capacitor as well as the reactor. Otherwise, we were already having these switched capacitor bank or even shunt reactor, switched capacitances, switched reactors. But if we use only capacitance, then it will only work as a capacitor. Reactor will only work, the shunt reactor will only perform the work of a shunt reactor, of absorbing the reactive power. But here it can do both. Or if you want to do both with capacitor and reactor, then we have to use combination of both capacitor as well reactor. And they have mechanical switches which can be used in different combination, and depending upon the voltage requirement, the reactive power generation or absorption, we can switch these different capacitances. So it's a capacitor bank. Several capacitors are connected in parallel and series combination is there. Depending upon the requirement of reactive power, these are switched. So here advantage of synchronous condenser is that wide range of field control, and because of that, it can work in both the direction, both the ways. The next is shunt reactor. Yes, we have already discussed in Ferranti effect to again bring the voltage back to its nominal value to reduce the voltage. We require this shunt reactor. It will happen generally happens in EHV lines more than 200 kilometers. Short overhead line when connected to a weak grid. In shunt capacitor, these are widely used in power system because they are the source of reactive power, and they are used to boost the local voltage. It is also widely used in distribution system, mainly by these industrial commercial loads. Because for commercial purposes, we have for commercial consumer, there is a penalty for poor power factor. If the power factor goes down, that means they are absorbing more reactive power. They are drawing more reactive power. Then they have to pay for that also. There is a penalty for that. And to avoid that, they will install these capacitor banks and boost the voltage at their point by supplying the reactive power. That is, it is mainly used for power factor correction. Main use of shunt capacitor is power factor correction. It can be permanently connected or via switch. Or there can be combination of capacitances, and depending upon the requirement, they can be switched. And here the disadvantage is that reactive power supplied is proportional to the voltage square. And when voltage reduces, the Q which is supplied is also reduces. It also reduces drastically. However, the grid code they require for the low voltage write through ability capability, it is required that the device should supply Q. So that is a disadvantage. Here, if V is reducing, Q is also reducing, but we want Q to increase during fault conditions. Then series capacitors, they are connected in between the line, in between the transmission lines. One line can be broken into two lines, and then in between a series capacitor is connected. For this, this is done within the substation. We need a substation there if you want to connect a series capacitor in a transmission line. The main purpose of series capacitor is to increase the power transfer capability from the for enhancing the stability limits, because we know this P delta curve. And this is the P max, and this theta, this will be equals to sine inverse of if we increase this P max, then our job is done, because the P is V or EV, V1, V2, V2, X sine delta. Now, if you want to increase this P max, then voltages are generally they are close to 1 by different types of these reactive power compensation devices used. We try to keep the voltage at around 1 per unit. Then X, we have delta and X to control here. Delta, we know that we cannot increase it much beyond a particular value. Generally lies between 30 to 40 degrees for stability purposes. Then we are only left with X. So if we can reduce X, then we can increase this P max. So this is P max. We can increase the P max. And series capacitor does that, because if this is a new reactance, existing was X. If we introduce this is if we introduce a capacitor, then it will reduce the reactance of the line. Using parallel lines also we can do, yes, we can do that, correct. If we use parallel lines also, then effectively we are, if this was X, if we introduce one more line of same reactance, then it will become X by 2, correct. So one way is this. Using parallel lines also we can increase the power capability. Another way is to introduce a series capacitance in between the lines. This will increase the, and because we are reducing the reactance, it will also reduce the losses. But it has certain disadvantages. One is series resonance. when starting the induction motor or synchronous machines. So for that, to avoid that, some resistance is connected in series in parallel with the series capacitor. Yes, subsynchronous resonance. It's a so widely. I think in 90s it was a very widely studied phenomenon. Low frequency oscillations. And then one another disadvantage is this hunting, this oscillation of machine around point. Then next one is static power systems. So they consist of the static power compensators. These are power electronic devices. Generally, they have this thyristor control react TCR is one, and TCSC is another. So they will consist of this power electronic device and also some switched capacitor or reactors. There, the static term comes because there is no rotating components here. The switching is done using these electronic devices, and all of their purpose is to maintain a constant voltage irrespective of the active power drawn or produced. So once we did this, all these studied these different types of sources of reactive power in the power system, then we discussed how if you want to study these the impact of reactive power, or we want to ensure that we want to see that these things are working properly, these different equipments are working properly, then we have to test them, validate them, simulate them, and try to validate them using some hardware. If we are to validate them using hardware, then we can be sure that they will work in practice also. Because we are using the same hardware which are used in the field, similar hardware, maybe of lesser rating, but we are using those. So we use these different types of real-time simulators. They are called real-time because they are able to simulate the model within real time, within the as per the clock speed. If we use MATLAB, so in MATLAB, if the model is very large in Simulink, if you would have seen in Simulink, if the model is large, then the time required, the computation time is also computation time we can say is proportional. It is proportional to the model complexity and size. If the model is more complex and it is large, then it will take more time to simulate the same model. But here we try to overcome that difficulty. Whatever may be the size of the system, these digital simulators, they will run it as per their clock speed, whatever their clock speed is. And the time step is microsecond. We can simulate even micro synchro phasers are there are also devices which are they are recording the phasers, they are synchronized phasers with the time step. So initially we had this SCADA system or this supervisory control and data acquisition. Yes. Now we have this PMUs. The PMUs use the synchro phasers. Here in SCADA we were getting the data. First one thing was here the rate at which we received the data was very less. Here we get within 1 second we can get several this data points. Another thing is here there was no timestamp. No timestamp was there. If I received a data, let's say of voltage, and so I received 1.01, whatever it is, for different values I am getting 0.95. But I don't know. In SCADA, we will just get these data. And in between, there can be some delay also because of communication. We don't know this data correspond to what time. And if we compare two data sets, let's say this is for bus 1 and this is for bus 2. And if we want to compare the data for the two buses, or we want to calculate the power flow between two lines, between wire, between a line connected between this bus 1 and bus 2, then we need the information of this angle. So with SCADA, we didn't even get the angles. We used to get this P and Q values. Angle we calculate. Here we get VI values. You also get phasors also. So here we get a phasor, voltage phasor, current phasor. Here we don't get voltage and current measurement directly. We get active power, reactive power measurement, and voltage magnitude is there available. But we don't have angle information here. Now, if you want to compare the voltage of two buses, and if we compare these two, we don't know whether they correspond to the same time or not. How can we compare the two values of different time? So that will result in our observation will be, or the conclusion that we draw by such a comparison would not be accurate. That's why the PMU was introduced. Here we have each data point which is measured using different these sensors, using these PMUs. They will be having a timestamp GPS based upon this GPS. So they have this GPS, this timestamp. We know at each bus at what time what data has arrived. Then we can easily compare them. With SCADA system, we use them for in these control centers for state estimation to know the what is the existing state of the system. What are the line flows? What are the voltage values at different buses, currents, everything. With SCADA, the state estimation was non-linear. But with PMUs, we have a linear state estimator. So that is another big advantage. Once we have linear things, it becomes very fast. We can estimate. We have different so many algorithms we can use. Convex optimization theory, all these things we can use. Here non-linear, it was non-linear. We had to form Jacobian, and all those non-linearities come up. And for such a large system, then Jacobian size is also very large. So that's the advantage of PMU. So just as PMU is giving us a very quick snapshot of the power system, similarly when we want to control something, we want to see, you would have heard of this term digital twin. Have you heard this term digital twin? Now it has become very popular. So digital twin can be used in different domains, different industries, like these autonomous cars, their battery management system, they can use digital twin. Yeah. In power system, they are right now being used for this wind turbine monitoring. So what is done that we have actual wind turbine located at a site. Okay, so we have an actual wind turbine which is located at one site. This is the actual wind turbine, and there are sensors, different sensors through which we collect data. For example, wind speed and wind direction. Then the speed of turbine itself, the rotation speed of turbine, power output, pitch angle, and everything different pitch angle. All these things we have different sensors, and these sensors are connected to the cloud, or somehow they are able to, through communication channel, they are able to send the data to the control center, or it can go to the cloud also. There we have a model, a digital twin. We know we have in we say two persons are twin. They look identical, exactly same. Here we have created a digital twin, a digital model of the actual wind turbine. Whatever the way this wind turbine is operating, that is captured using a mathematical model and is there in the maybe some RTDS, whatever simulator is there. That model is available, and we are getting that model is getting data using these different sensors which are there on the actual wind turbine, and then it can give output again to these actuators. If there is some problem, so we can keep a track of the actual wind turbine, and while sitting in the control center we can take certain actions on the wind turbine. We can optimize its operation. If it is too windy, it is a storm, then we can stop its output. We can change the pitch of the blades and save the wind turbine. If there is some malfunction, we can know very quickly and try to address it very quickly. So all these things in real time, we will get the data, the status of the wind turbine, and we can even control it through that this two-way communication. It's a loop, hardware in loop system. Okay, is it clear? Same thing can also be done for autonomous cars or the battery management system within the car, or even the entire car also can be controlled in that way. Then, yeah, we were discussing this digital real-time digital simulator. These are very important. So suppose we want to test a new hardware. We cannot directly go and connect it to the power system. Especially if you want to test something at a very high voltage level in transmission system level. Let's say at the transmission level 132 kV level, I want to connect a new solar farm or wind farm, and I cannot go and simply connect it. Just create it and directly connect it. Before that, we have to do several studies. How that connection will impact the grid? Will it create any problem? Different types of feasibility studies are done. Several detailed simulations are carried out. If we can model that grid in a system and we have a small hardware of the actual hardware which we want to connect, then the model of the grid is available in the RTDS, and then we can the actual hardware can communicate with it. Or another example is the digital relays that we have. Let's say in the transmission line, I want to install a new digital relay, a numerical relay, then I want to test it before installation. Then I can model the transmission system in the RTDS. Or RTDS is primarily used for power system applications. In RTDS, we can model the entire transmission network, and at that particular bus where we want to install that relay, we can connect that relay to the hardware through a power amplifier. So, do you know why power amplifier is required in hardware in loops? The output of these RTDS or any digital simulator is generally within 0 to 5 volts. The analog output. So here in RTDS we have in RTDS we have different cards. These gigabit transceiver analog output, gigabit transceiver analog input, digital output, digital input. These are four different types of cards which are available for taking digital or analog output or input. From RTDS, we will get an output of only 0 to 5 volts. Whatever input is there, let's say I want to take the voltage out and I have a relay. The relay requires both voltage and current signals. And then it will do the DFT. First, that relay will convert them. It will have a ADC block, convert these analog signal into digital signal, and will perform a DFT. And then we'll find out the voltage and current phasors from that. And it can continue tracking it. And there are different algorithms for fault detection based upon these phasors. And once the relay senses that there is a fault, it can issue a trigger signal. And this trigger signal is a control signal. Okay, so we're talking this voltage will be, let's say, inside the voltage was, we were operating at let us consider only the distribution system. For 230 volts, we have the line to neutral voltage, we have the phase voltage is this. Okay, 230 volts. But the output will not be this 230 volts. The output from the RTDS will be, let's say, 230 volts corresponds to 5 volt. It will not correspond to 5 volt. If it is 230, it 230 root 2 will be used corresponding to 5 volts. So it will be 5, let's say 230 will be 5 by root 2. So we will get this voltage as the output. But this relay which is there, it requires all the three phase voltages VA, VB, VC. And these are in the range of 230 volts. But the output from RTDS is only 0 to 5 volts. Now what to do? But we want to give output of this. Initially in RTDS, we were simulating 230 volts. But the output of RTDS is only 5 volts, limited to only 5 volts. Now I want to give this output to a numerical relay which requires a 230 volts input. So how to make this 5 volt into 230 volt? That is done using power amplifiers. The signal which we are receiving here, it's low in the power content. Its power content is low. The power amplifier will amplify that signal to make it suitable for the operation of the actual hardware, which is the relay, digital relay. And then it will do the processing, and finally it will issue a trigger signal, a control signal. And this control signal it is a digital signal, or it can be analog also. But this control signal are in 0 to 5 volts only. You can directly give it to the RTDS. But in between, we need this power amplifier here to amplify the signals. Because these simulators, they will not produce a real signal. Although we are simulating a 66 kV grid, a 132 kV system, or even 765 kV, the output which they will provide will be scaled to 5 volts. If you want to use those signal again, then we have to amplify them. And for that, we need the power amplifier. Is it clear? So now if we wanted to test this relay on actual system, and if the relay was not good, it was not performing as per the desired specification, then the system would have been impacted. Before directly connecting any equipment to the system, we can do these type of analysis on a model of the system, which is created within these digital simulators. They will mimic as if we are working with the actual real the real world system. And the loop which is running here, this is the model in RTDS, and here we have some controller or some other hardware. They will communicate with each other at a very small time step, microseconds. So everything is happening in as if it is happening in real time. Well, it's very fast. That is the advantage of using these. So we cannot do the same thing with MATLAB. MATLAB is very slow. So RTDS does a nodal analysis. MATLAB works in state space. Here we have these processors, and they have 3 cards per rack, and each card can have 72 single phase node. So if we have one rack, in one rack we have 3 cards. They can model a 24 bus system. One rack can model a 24 bus system. So 24 bus three-phase system. In three-phase, each phase will be having three nodes for each phase. So each bus will be having three nodes for three phases. So we can model these 72 nodes. Single phase, so we can use three phase. If you want to model a big system, then we need to increase number of racks. And another thing is when we have limited racks, then and if you want to model the entire grid, we need to then, let's say the entire grid has 7,000 nodes and the RTDS which we have only supports 24 into 6, 144 nodes only, buses only. Then we need to reduce this network into 144 bus system is to aggregate several nodes to form one node so that 7,000 nodes network can be converted into 144 node system, still representing that actual system by doing aggregation in such an intelligent way that it still behaves as if we are simulating the bigger network. Certainly, we will not be able to see the each and every minute details, but on an aggregate level, we can do that. It depends on what we are trying to observe. Okay, so these are different types of simulators. This RTDS is primarily used for power system applications. And Taifu, this is used for this DC microgrid simulations application. It contains detailed model for distributed energy resources, detailed converter models. And then OpenRT is another one. It can be used for power system and power electronics, but it is more widely used for power electronics. In power electronics, we need these switching pulses, high frequency switching pulses. And these, the new power electronic devices like these GaN based gallium nitride and the silicon carbide, their switching frequency is quite high. We need a simulation time step of in nanoseconds also. In that case, the polarity is used. RTDS simulation time step is in microseconds. Yeah, simulation corresponds to the real time clock speed here. And these are the different hardware in loop simulations. This is the loop which is shown. Can you, I think you are able to see the picture here. So this is the control hardware in loop. This is hardware in loop and this is PHIL. This is power hardware. So this is similar to what we were talking about digital twin. Yeah. Here you can see there is the actual model is within the RTDS. And from here we are giving the voltage and current measurements to the this card, GTO card. Through the GTO card, this is in RTDS itself. We are taking output from this card and giving it to a controller. And this controller is using these signals to generate these control pulses for the operation of these converters within the model. So it's a loop. Here in the loop, there is hardware. Hardware is this RTDS is hardware. And control, it's a control hardware because this loop is completed by this controller, which is a control device, not a power device. It's not a hardware. Since it's a hardware, we can say, but it's only from this we are only generating the control signal. The input here is only control signal. The plant is within RTDS and controlled using some external controller. Now this is hardware in loop. Here we are integrating the hardware, actual hardware. So this is the actual DC microgrid here. You have battery, supercapacitor, or it's a PV emulator. This is a PV emulator. So these are real hardware devices. And this is a real DC microgrid created actual hardware and which is connected, which is controlled. And the controller is within RTDS. Controller here is within RTDS. Here there is no hardware. Here we are not, that hardware which we want to test, we can say it is sitting within this RTDS. The actual system or hardware is not tested here. It's the model only. Let's say we want to do, we are doing some grid integration study. Grid integration study. And we have modeled the system within the RTDS. We have a solar farm connected to the grid, modeled in this RTDS. Now I want to control this solar farm so that I want to check the MPPT algorithm working, whether it is working or not. I wanted to implement the MPPTs. So that control logic I can design here and generate here and then give the output as control signal to this the solar converter which is interfacing the solar farm to the grid. That can be controlled using this. Now here the system here it is different. Here we are trying to see whether the DC this microgrid is able to perform its operation or not by using the actual small scale microgrid. This is the actual microgrid and we want to test the control logic, whether the microgrid is able to do equal power sharing. Let's say it is able to maintain the state of charge of battery, whatever algorithm which we have designed to do the centralized or decentralized control of microgrid, are we able to do it, whether it is performing well. We can check that by designing the control algorithm within RTDS. The algorithm is in RTDS and that it is able to take input from this microgrid. So now microgrid, this is a real microgrid. And the output of this microgrid, the voltage current measurements, they will be in the range of, these will not be control signal, these will be power signal. And if you want to give those input to RTDS requires only a 0 to 5 volt. So in between we need a power amplifier. This is the power amplifier. Or it can be even the grid emulator also. It can be the grid emulator also. But the RTDS, it requires only 0 to 5 volt. For that, we need to convert the signal from this power to control signal. For that, also we need to reduce the voltage level. Or if the control signal are directly available, we can use them directly. But if not, the voltage and current measurements, they are not control signal. For that, we need this. Here controller is present in RTDS or these different types of digital simulator. And the hardware which is outside RTDS, it receives control signal from RTDS. RTDS will generate the control signal to control these equipments. The power hardware in loop, then this is close to actual validation. This is similar to digital twin. So here the part of system is in RTDS, and so here what is happening here, the system is which is under test, or the hardware, it is not, it is only the control logic. Only the control algorithm or logic is within the RTDS. But here, sorry, in PHIL, a digital twin, if we consider the digital twin, then a model of RTDS or the actual hardware, the model of actual hardware is, this is the actual hardware, and it will communicate with its digital twin, which is within the RTDS. If it is digital twin, otherwise a part of this hardware and a part of bigger system can be within the RTDS, and the rest of the system can be this actual hardware. That is also possible. And they will integrate with each other they will communicate with each other through this power amplifier only. So that will be able, that will allow us to complete this loop. Here difference is here if you see the entire system, here the entire system is within RTDS. And the control logic is in the outside, it is outside in some controller. Here what is happening? The hardware, the system is outside. And the control logic is in the RTDS. Here the system can be both outside apart and then RTDS. And control can be in RTDS. Or there can be some other controller also, external controller. Both is possible. Both are possible. So here this hardware under test is controlled either using RTDS or a separate controller. So this is the difference between these three. I hope it is clear. If it is not clear, you can ask once again. Is it clear? Okay. Then, yeah, then this was the case study which was presented. For that, we studied all those things. This was the case study that how to do a coordinated voltage control. So for voltage control, we need to control the reactive power. If voltage is going down, the reactive power needs to be supplied. Or this voltage control it can be done by using different, so many elements are there in distribution. So this is for a distribution system. In this lecture, this IEEE 33 bus system was used. It's a distribution system. Capacitors mainly for voltage control, you're saying? Yes, okay. Yes. We can use capacitors, but generally we have these in distribution system. These are radial systems, right? And capacitor are generally used to do a local control. Power electronic devices are there. They are generally used by the consumer itself. They will provide a local control, better local control. But if you want to improve the voltage profile of the entire feeder, then the other devices are used. OLTC is used, so on-load tap changing transformer. If we have this is a source bus, and this is one feeder, and several loads are connected here. And because these loads are connected, and we know that R by X ratio is quite high in distribution system, resistance is more. The voltage drop is uh, more. Voltage drop, maintaining voltage profile in distribution system is very big. Is the main concern. So voltage regulation is a major concern in distribution system. Yes, here we have this OLTC on the on-load tap changing transformer. If the voltage here is reducing, we can change the tap and boost the voltage, increase the voltage. The voltage profile will improve. But it is a mechanical device. Right? It is a mechanical device. Because switches are mechanical, so it's a all, and we know mechanical time constants are large. Therefore, they operate slow. Their operation is slow. So here it is called a coordinated control scheme because we are coordinating different types of devices. Here, two types of devices. One is this OLTC, which is a slow device, and there are some fast devices also. This microgrid. Then these wind converters, they have this grid side converter. If it's a DFIG based, then there is rotor side converter and one is a grid side converter. So this grid side converter can be used to help the grid, to support the grid. And they need to actually they are supposed to be supporting the grid as per the grid code. They need to supply reactive power when there is a voltage drop. That we call the low voltage LVRT, low voltage ride through capability of these converters. All these converters are equipped with this LVRT capability. And then D STATCOM is also there. So all these devices are very fast devices because all these are based on, as you correctly said, based upon these power electronic switches, which is very fast. Their switching frequency is quite high. But they will operate very fast and the OLTC will operate very slow. It will not be used properly if they act before, because before OLTC is slow till the OLTC will do something. These fast reactors, these fast acting devices will do their work, and they will not be able to improve the voltage to the optimum level because OLTC has not been able to do its work. OLTC is able to boost the voltage by changing the tap. It's not altering the reactive power as such. But other devices, they are trying to inject reactive power to boost the voltage. These are three different states which are defined. One is steady state, where there is only small switching of loads, very minor fluctuations, and the reactive power supplied by these fast acting devices is restricted to less than 40% of their rated capacity. And this in steady state, the voltage will be within 0.9 to 1.1 per unit. In dynamic state, the voltage is same between 0.9 and 1.1 per unit. Here it is dynamic state. In dynamic state, there can be sudden load switching. And here the reactive power support is limited to 40%. Exactly 40%. This is transient state. Here faults are there. In case of fault, voltage will dip. Suddenly there will be a voltage dip. Voltage will dip to a very small value. In that case, these fast acting devices are allowed to inject. They are supposed to inject 100% reactive power because voltage is very low, and we want the voltage to come up to the nominal value as fast as possible, as quick as possible. And that can be done by injecting the reactive power. So this scheme has these three states. First, the identification of the operating condition. Which state is this? Steady state, dynamic, or transient? Based upon that, the action will be taken. Because based upon that, it will be decided who will do what type of action. So these two, OLTC and DC microgrid, they operate in steady state and dynamic. And while these two are available in all these states, then once we know all these things, we need to introduce the delay because we don't want the OLTC, these fast acting devices, to act before OLTC works. So OLTC will not be used if they work very fast. They operate so fast. So we want a delay so that OLTC can do its job, and then the remaining part can be done by the fast acting devices. So time delay is introduced in the operation of fast acting devices, which is as per this. Then these were the two different schemes. These two is these two are common. Time delay is there, and 40% deadband is there. 40% based on reactive power injection in dynamic state. And then reactive power, this in this improvised scheme, two other things are also there. Reactive power, when it is waiting, there is no reactive power injection here, but here there is a negative reactive power injection. That means it is absorbing reactive power. And then waiting period for all the voltage mismatches here, it is same for all, but it is not same. It depends upon the voltage. So this bandwidth is considered. There is no time delay for above this voltage. Then next thing which we discuss was this power system security. Power system security is a very important thing. We want the system to operate even when there is some failure of component. These are the different practices to keep the system operating even if some component fails. So we want to ensure that beforehand only. For that we need to prepare the system, operating system, so that any credible event. And this is done using the contingency analysis. The credibility of the event will be decided based upon this analysis. All the different types of events, they will be studied, and then they will be considered as a credible or incredible. Not all the events will be all the event will be very serious, or some events might not even have any major impact. They can be avoided. Once we do this contingency analysis, we get to know that these events are very important. And if they occur, they can have a major impact on the system. Those events will be filtered out and they can be studied more detailed in detailed analysis can be done. It all depend upon the contingency analysis generally is done on its is beforehand only, not in real time basis. Because so many events are there. This classification of events can be done beforehand. But for a large system, it will see the three different approaches. Here, we want the system to operate for any credible event so that it is not in any emergency situation. Also, to ensure the system is prepared, we always keep the equipments, their operation within their specified limits. Because if they violate limit, if we allow, let's say, the thermal capacity, the transmission lines have a thermal capacity. And if we allow the line to continue carry the current which is beyond its thermal capacity, then it will melt and the system will have a major impact. We want to adhere to these operational limits of these different devices, equipments. And as soon as these limits are hit, the system should throw an alarm. Yes, this line is getting overloaded. We need to do something. So the control center, we can see all the lines are being monitored by persons who are sitting within the control room. They can get the real time picture base. What is the loading limit with respect to thermal limit of the line? The loading limit, I didn't understand what is loading limit. Somewhere I read it is 60%. And so you're saying thermal limit is 60%, or is the thermal limit of the transmission line is, yes, I have also been, it's 50 to 60%. Safety factor is kept. Yes, it is around 50 to 60% of this actual rating of the line. And a safety factor, that is a safety factor which is considered, because if we do not have that safety factor, there are durations when the limit can violate. Suppose, just as what I was saying, in control system, a person is sitting. There is one transmission line between bus 1 and bus 2. And the control system, that state estimator, it is showing that this line is getting overloaded. It is showing overloaded, 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 overloaded. Alarm is there, red. Now, when the alarm is there, the line is in the overloaded condition. It is hitting its limit. If we do not keep that that safety factor, then as soon as we see the alarm, the line will melt. We cannot operate it at 100% limit to avoid such situation, because emergency situations are there. They're always there. That safety factor is kept. That 50% they are loaded only to the 50% or 60% of their thermal capacity. Even if so, this will definitely, it will happen only for a very short duration. They are designed for that only. But for a shorter duration, they can uh, carry a large amount of, means twice 1.5, 1 point or 1.8 times their actual rating, but only for a short duration. And within that short duration gives enough time to the operator to take some action to again bring the uh, situation under control. We will try to divert the power, reroute the power, uh, do some optimal dispatch of generation, do something. They have a lot of experience. They'll do something with time. I think line thermal limit also reduces. Yes, it depends upon many. Even on the same day, even in a day also, the thermal limit changes. It is not constant for the day because it depends on temperature also. If temperature outside is high, then thermal limit will reduce, because that uh, heat transfer is not, temperature outside is very high, so heat transfer is not much. It requires temperature difference for that thermal conduction. That is why dynamic line rating is some companies are trying to do this dynamic line rating. They have come up with some devices also. There is one device, I don't remember its name, but it's kind of a circular spherical ball which is connected over the around this conductor to measure its temperature and everything. So many things to estimate the dynamic line rating. So it's not a constant thing. It keeps on changing. Depends on many factors. It depends upon loading condition. Depends upon temperature. It depends upon, yes, with age also it changes. There are different factors. Aging, yes. With age it will change. It will change. The strength of the conductor will also change. That's why we need to operate these line within a safe limit, a safety factor. That safety factor can change. The older the transmission system is there, then its capability to withhold these overloading situation for a larger duration of time, that reduces. That also we need to know what is the actual thermal rating now of the transmission lines. That's very important. So we need to prepare that. These are the different operational limits. We need to check them and keep the equipment within these limits so that any emergency situation doesn't arise. Then N-1 rule, N-1 is the most economical one. You can go for N-K rule, but then economics, you have to compromise with the economics. It will be very costly. So N-1 rule it says that if any one outage, any one component of the system goes away, then with n-1 component also, without that one component also, system should be able to work properly without much deviation from its normal state. If there is a generation outage of a very big generator, let's say recently there have been several phenomena, like in which country I don't exactly remember, either maybe it's in Europe, it's a European country, maybe Norway or some country. There was a for many several times there was outage of this nuclear power plant. Around 2 gigawatt, 2.5 gigawatt of nuclear power plant. Suppose a grid is in grid, suddenly there is a loss of a generation of 2.5 gigawatt. It's a very huge amount, 2.5 gigawatt. There was a very huge dip in the frequency. I could have shown you the graph. I didn't remember while preparing the slides. Next time, maybe I can show that there was a huge dip in the frequency. And then the operator had do to do some take some action to bring the frequency back to its nominal value. It took some time to bring the frequency back. So these operating reserves, these ancillary services, they come into picture to handle this. The primary, secondary, and tertiary ancillary services. As soon as there is some frequency drop, the inertia will come into picture. Then primary frequency response. Then if it is not able to bring the frequency back to within a range, then secondary will come up. If they are also not able to do, then tertiary frequency reserve services, they are used. Yeah, load shedding can also be done. If it is the frequency is way beyond the control, then load shedding is also done. It is also done. So somehow we have to use as a final step, correct? So somehow we want to have balance this generation and demand. Entire system is working very tightly to bring this generation and demand in a very close, very tight band is kept. The frequency also has such a very, it has a very tight band, 49.95 to 50.05. So 0.1 band of 0.1 hertz only. So ensuring that it requires so much control. So we want to make sure that if one generator goes out, it doesn't result in the tripping of other generators, because one generator goes out, frequency will drop, and all these generators they have this under frequency this under frequency relay. Frequency goes below that 49.95, they will trip. The generator will trip, and then frequency will further reduce. Then there will be a cascading failure. Similarly, it happens with lines also. That 2012 blackout, it happened like that. One transmission line, there was an overload. There was an overload, but the relay saw it as fault. It was load encroachment problem. So overload relay thought there is a fault. The line was taken out. Because of that, there was overload on other lines. That line was taken out. As a result, there was a cascading failure of the transmission system, and the northern grid, northeastern grid completely collapsed. So these cascading failures we want to avoid. So these are there were functions, three functions of system security. One is system monitoring. This we will study in the next week. System monitoring. This is done by this state estimation. Now we have these PMUs. Actually, now we are in a state where we have a mixed system. We have SCADA system plus PMUs also. We don't have the PMU is not installed on each and every substation. We have PMUs on 400 kV and above. Now they're trying to have them at 230 kV also. That is the next phase of PMUs. So 400 kV and above substations have this PMU. Remaining they are still operating with SCADA. How to combine these two data, that is another challenge that we will see in hybrid state estimation. How to use these two data to get the picture of the system. This is the system monitoring, and then next was the contingency analysis. And last one is the security constrained optimal power flow. Did you understand what is this security constraint OPF? Okay, good. I think we can move ahead then. We'll discuss with questions that LODF numerical is important. It is. We'll spend some time on that only. I think it's better to spend time on that numerical, right? 6 questions are asked. Yeah, okay. Okay, it has a. Okay, we'll just. I think 2 slides are left with. After that, we'll take that question only. Yes, so security analysis approaches. We have these 3. One, to have fast algorithm using linear approximations. From here only we go to this sensitivity analysis, LODF, and which one is other? Uh, the 2 distribution factors. Do you remember? Yes, PTDF, correct. It is obtained from the generation shift factors. Power transfer distribution factor and load outage distribution factor. One thing is to use this fast algorithm, which are these will be based upon linear approximation of the power system, and they will use the DC power flow. Because these are linear, very fast, we can cover almost all the cases. Then approach 2 is to use traditional approaches, but only consider important cases. And these important cases can be identified by doing that contingency analysis offline, based upon the data which we have, past data. And then third is parallel processing. Improve this traditional method so that we can gain the speed for larger selection of cases. So this is in between approach 3. Approach 1 will be very fast, but it will give approximate solution. This will be very slow, but give a good solution, near optimal solution. This third one is in between. These are the sensitivity factor. They are useful for an approximate analysis of effect of each output. This is approximate because it is based upon the DC power flow, which is a linear approximation of the non-linear power flow equations. Here we can only get the active power flow, not reactive. So they will show us, we'll see. So these are the 2. One is generation shift factor. From this, we can also derive the power transfer distribution factor. The generation shift factor will tell us what is the change in line flow. Let's say there is one injection happening at a ith bus, and let's say this is some K and L bus. So K, let's say M and N, and this is some line L. So this generation shift factor will tell us. Sorry, let me connect charger. It will generation shift factor will changes at what will be the change in the line flow when there is a change in injection on some bus I, and the load distribution load and PTDF is when there is a transaction happening between two buses. Injection happening at ith bus, withdrawal at jth bus. How the line flow will change on line L. Power flow will change on line delta F on line L. That so here it will be transaction between I and J for PTDF and load outage. Then if this line goes out, yes, line outage, then what will be the change in the power flow on that line? Okay, so we'll see the question directly. Let us. If these are simple questions, we'll take them later. Let us first directly go to the numerical. Well, if time is there, we will see those questions later. Okay. This is the question. It is similar to what is there in the uh, assignment, but it is not same. It is this question I have taken from this Wooden-Willenberg exam unsolved problem. In the assignment problem, the line is here in between this. In this, the line is between bus 2 and 4. Assignment you will find it is between 1 and 3. Also, the values are different. Generation and load values are also different. Assignment you will find this is 30, 30, 30. Here reference bus is also changed. In assignment you will find a reference bus is 1, and this is here reference bus is 2, or the slack bus here is 2. Sorry, this is not correct. This should be 2. So bus 2 is the slack bus here, and bus 1 we have a generation of 150 megawatt. Bus 2, bus 3 and bus 4 having these loads of 220 and 280. Bus 3 or bus 4 I have interchanged. Right. Have you seen these problems at the back of this Wooden-Willenberg book? Yes. This same problem? The problem is their answers are not given. I think. Okay. Just make it. This is 280 and this is 220. Because I have solved it like this only. Bus 3 220 and bus 4 is 280. So first of all, what you have to do, you can follow the same procedure which I am following, which we are following here. So we want to, all these things are given, we are given the impedances. Between 1 and 2, it is point J2. 1 and 4, it is point J25. 2 and 4, it is point J3. 2, 3, it is 0.15 and 0.4. We can say this is minus J5 minus J4 minus J, how much? This is minus J 2.5 minus J 3.33. This will be 6.6667. So can you tell me, can you help me with Y bus? What will be the first element? Y11. You can remove this one. Not this. What will be Y11? Yes, minus J and J I have taken out, so it is 9. Then it will be 5 because of diagonal element as yes plus 5, it is minus 1 minus times of that element. Then between 1 and 3 there is nothing, 0, correct. 2 3 4 is 4, correct. Then 2 1 is 5 because it is symmetric. Diagonal element 2 2 is here, 5 plus 6 6, it will be 11.667 minus. Then 2 3, oh, did I make a mistake? Is Y22 correct? Yes, it is not correct. I missed one element. I missed one element that it will be for 15 only. It will be minus 15. Then this will be how much? 2 3 is point. It will be 6.667 20 by 3. So this is, and what is this? 3.33, correct. Between 2 and 4, 3.33. And this one is 0. No, sorry, 2 3. 3 1. 3 1 is 0. 3 2 is 2 3. 6.667. 3 3 is diagonal, which is 8 point. How much is this? 2.5 plus 6.66. 9.1667. Then 3 4, between 3 and 4 it is 2.5. It will be minus. Then this is same. I can 2.5 and last 4 is 4 plus 2.5, 6.5 plus 3.6 plus 3, 9.833. Okay, yes. This is Y bus. This is Y bus. But for we want to calculate flow on these lines. LODF, for that we need the flow also. Actually, for LODF, we have a direct formula. We don't know. We don't need the flow, but we need the B inverse matrix, which we use for the DC power flow. And that B inverse, we know that B is minus times the imaginary of Y bus. Last time we had also discussed this. While it is not same as the Y bus, we have to multiply it with the minus. So B will be this minus times, remove J and multiply it with by minus. So all the diagonal elements will become positive and the off diagonal will become negative. So this, do you need all buses? All buses for B inverse you're saying? I mean slack bus also. This is our B bus. Sorry. For B inverse we need the reduced. This is full B. We need the reduced one. Remove this, the row and column corresponding to the slack bus. Here slack bus is bus 2, not the bus 1. If the bus 1 was there, then we will get a 3 by 3 matrix. If bus 1 is the slack bus, and let me just change the color. If bus 1 is the slack bus, we will get this matrix, this submatrix 3 by 3 matrix. But here bus 2 is the reference bus. We need to remove these, this row and second column. Then the remaining will become the B matrix. You can see here. So we have done this one and this part. So this B dash is this matrix. Okay, this is B0 and B dash is after removing this column and this second column and second row. Okay, we are left with this. But calculation of inverse is difficult in exam. In exam, do you get online calculator, right? But you cannot use offline calculator. You will have to do it manually. It will take some time. And if practice is not there, you can make some mistakes also. And that is a problem. That is, yeah, but uh, if it is a 3 bus, I think in exam, if 3 bus is given, then it is better. I don't know. It will be, whether it will be a 3 bus or a 4 bus system. But yes, we'll see the procedure. But you try to practice with the 3 bus, taking inverse of 3 bus so that you don't make any mistake, calculation mistake. Just keep a habit of that. But hopefully we'll get only a 3 bus system. Yeah, it takes time. That is correct. It will take time. Also, if practice is not there, it is prone to error. You cannot even verify. Okay, so we have B dash. Then we can calculate. Now we have these three angles. Theta 2 is already 0 because we have taken it as a slack bus. We don't need it. Then theta 1, theta 3, theta 4. And P1, P3 and P4. B inverse we can calculate, B dash inverse. P1 is 1.5, P3 is minus 2.2 and P4 is minus 2.8 because there is no generation here, it is only demand. We are only this P matrix or P vector, it is injection. It's a injection vector. This also you need to keep in mind. Don't blindly just take it as 1.5, 2.2, 2.8. This is 2.8, this is 2.2, this is 1.5. All these P vector should always be injection. If it is demand, then injection is 0 minus that demand. So it will become negative injection. Okay, so these two are negative. Loads are negative, correct. So they are negative injection. They are not injecting, they are drawing. That's why they are negative. If you forget that value, that negative, then you will get this angle all positive angles, and they will be very large values. And once you get very large value, you can your bell should ring within your mind that angle cannot be such large. Generally, we'll see angle will be less than 1 radian. Here we see it is 0.3 radians. But if you take both P3 and P4 is positive, we will find something 3 point something. Uh, no, sorry, not point. Because but you will get some large value, some 0.5. All these values at 0.4, 0.3, 0.5. All these values will never be so large. Generally, they are not large, and you'll find always some angle will be negative. Some will be positive, some will be negative because one we have taken at 0. All of them will not be positive. Okay, we can calculate this and then we can calculate the power flow. So for LODF, this matrix is very important, B dash. We need this matrix. So calculate this matrix very carefully. This is one method of using the Y-bus method matrix. Another we discussed last time, right? Do you remember this? We discussed this. You can calculate B like this. You transpose BD into A. Yes, so you can use that also. Then this negative and all these things, uh, everything will be taken care simply by this. And flow also you can calculate directly. Okay, so for LODF, this is the main thing. This is not required. You just calculated. This is not required for LODF. For LODF, B dash is the most important thing which is required, and its inverse is required. So first calculate B dash and then calculate inverse. The inverse of B dash. This is the X, but include this 0 also here. For slack bus, introduce this 000. First calculate B dash and then include 0 for the slack bus. That row and column corresponding to the slack bus, make them 0. This will become the X matrix. This X matrix and the individual X values, the impedances, they are the only two things which are required for calculating the LODF value. Okay, is this fine up to this point? Is this okay? Okay, so here we can see this is the formula. So this also, this you need to remember for calculating LODF. Delta PLM, and this is the line which we are monitoring. The change in flow which we are monitoring for this line, and this is the line which is under outage. This is the line under outage. Okay. RS is the line which is under outage and LM is the line which is being monitored. And this is the formula, the XRS divided by XLM. These two are the impedances, small x's. And capital X will come from this matrix, B inverse matrix. So this is XLR minus XLS. First take this one. So line which you are monitoring. So XLR minus XLS minus XMR. M is also for the line which you are monitoring. So this is the line under monitor L. Not let us call it as L head. And it is connected between these two buses L and M. And the outage is happening of this line K, which is between these buses R and S. This XLR minus XLS minus XMR minus XMS. divided by small x rs. Small rs, the line which is under outage, its impedance here, minus xrr, x minus xrs minus xsr plus xss. So here L is, we want to find out LODF on line 1 2 for a outage of line 2 3. So here R is 2. Here R is 2. So line which is under outage, R is 2 and S is 3. And line which we are monitoring is LM. It is 1 2. Now we can just substitute all the values. We can calculate. We already know x23 by x12. Here it is diagonal. It is same. x23 will come here. x23. So first of all these values are for the line which we are monitoring. So first index corresponding to the line which we are monitoring. Line which we are monitoring is 1 2. So we'll make x12. Sorry. x12. So take L R minus LS, then MR minus MS. So L, so let us first write this is L, M, and this is R and S. So L is here 1. You can write it like this also. L is 1 so that you remember. Don't make a mistake. Explicitly write it that why max limit are not required. Max limit are not required in this for calculating LODF. That is not required. We can calculate it without that. Okay, so and R is 2, S is equals to 3 here. So just calculate all these values. Okay, so x12 minus x13 minus x22 minus x23. So take first L is equals to 1 and R is equals to 2, S is equals to 3. So LR minus LS minus X MR minus MS. So M is 2, then R is 2, R is 3. And here x23, it is same diagonal minus x22, which is RR. R is 2 here. So 2 2 minus RS 2 3 minus SR 3 2 plus SS, which is 3 3. Okay. So we substitute all these values. X12 and x13 we know. It x12, 1 2 is 0. So x12 is 0 and x13 is 0.164. And x22 and x23 are 0. X is a no X, which X, capital X is a 3. It's a 4 cross 4 matrix, right? Capital X. This is a capital X. After introducing these 0 elements for the slack bus, it's a 4 cross 4. Because you will find LODF for lines. Lines are connected between all 1 to 4 buses. There are 4 buses. So it can be 1 4 here also, 3 4 also. So if you now want to find out x14, and if you have a 3 cross 3 matrix, how will you find x14? Right? You will not be able to find. The x, please remember that x is a 4 cross 4 matrix. So it is calculated using B inverse 3 cross 3 matrix, and then for the slack bus, the row and column corresponding to slack bus are written as replaced by 0 element. So please remember this. In the assignment problem, you will have to introduce Inverse is to be, no, you need, no. You are creating a, you are getting confused. What you have to do, you have B dash, right? We have already found B dash. B dash is a 3 cross 3 matrix. This one, this is B dash. Now what you do, take inverse of this B dash. Inverse. Okay. It will be a 3 cross 3 matrix. Inverse. Now X matrix is not this. X matrix is this B inverse plus, this is a 3 cross 3 matrix, but X is a 4 cross 4 matrix, where this second row, second column and second row are replaced by this 0 are added in this matrix. Zeros are added. After adding these zeros, you will get a 4 cross 4 matrix. This is the final X matrix. Is this clear now? This is very important. Yes, inverse is 3 cross 3 only. We are adding zeros in that matrix corresponding to the slack bus. The row and column we are adding a 0. Okay. So in this way you can calculate. Is this clear? Okay, good. So I will upload this PPT. You can go through them also. And similarly, this is for line 1 2 when outage is on 2 3. You can, sorry, line 3 4, outage is on 1 4. You can calculate that, right? Same formula. Matrix is also same. Only these values will change. You can calculate. I hope it is clear. Now you'll be able to do all these 6 questions. Follow the same procedure and you'll be able to solve. Clear? Just let us quickly go through these questions. So underground cable are usually a source of reactive power under usual loading. Is this true or false? Yeah, true, correct. Then disadvantage of using a synchronous condenser is that it has a wide range of field control. Is it a disadvantage? False, it's an advantage. Synchronous condenser increases the short circuit capacity of the system. Is it true? True or false? It is true. It is disadvantage of synchronous condenser. Because when, yeah, okay, then synchronous condenser can work as a shunt reactor. Is it true or false? It can work, right? It can work both as a capacitor and reactor. When overexcited, synchronous machine work as a source of reactive power. This is also true. Then overexcitation causes increased eddy current loss. Is it true? Correct. It happens at under excitation. Hunting of synchronous machine may occur at light load due to low R by X ratio of the feeder. Is this because of low R by X ratio? No, false. Okay. So do you have any other doubt? Not, then we'll meet next Tuesday. Thank you very much for joining. We will meet next Tuesday for the state estimation topic next week. Thank you.